And it worked. We have our lecture. Woohoo! Thank you, thank you, thank you. Yes. Okay, welcome to the seminar. Thank you for turning up on behalf of the cookies. Absolutely, yes. My name is Johannes Herman. I'm giving this talk on behalf of the CIS, Computational Intelligence Society of the IEEE, which is, by the way, an advertisement saying, join me, join my jihad. I know that's politically incorrect, but because it's a very neutral organization, I think I can get away with that. If I said that for, say, the Red Cross, people would probably be a bit cross. So we're going to talk about a quantum of computing. So just a certain amount of computing and a whole lot of other stuff as well. Quantum computing is, frankly, mostly physics. If you look at most of the quantum research centers, you look at their staff lists, there's not a whole lot of actual computer scientists on there generally, although there may be some exceptions I haven't looked at a lot. But the idea is, I actually quite like this, because I always thought quantum means a really tiny amount, or maybe a really big amount. Some definitions say that, but this definition basically says it's like, you know, a share or portion. The last definition, that's the one I like. Now, as I mentioned to some people coming here, I've had some fairly serious computer issues while putting this thing together, so I've lost a lot of slides and have put them back together again. Hopefully I've got the comics at the end, but I don't have a couple of the intro slides. The intro slides are basically who am I, who's the IEEE, and why the heck are we doing this seminar in the first place. So I'll do that off the top of my head. I'll see if I can remember who I am and fill all that in from scratch. It's actually fairly pointless since most of you are my students, so hey. But hey, you know. Yeah, I'm lecturing computer science, and this semester I'm doing a unit called Theoretical Foundations of Computer Science, which is a really nice unit, by the way. Just give it a bit of a plug for those people looking for optionals. Basically, the unit is all about computability and complexity. Can you actually solve this problem? And if you can, well, how hard is it to solve it? Now, when I've been teaching that unit, I've taught it before when I was in Malaysia, and I taught it last year here, often I'm saying to students, well, now this is the case, but this is only the case for our standard architectures. It doesn't necessarily apply to other things, such as quantum computing, the genetic computing, etc., or biological computing, whatever you like to call it. So this year I actually thought, well, I'll put a lecture on quantum computing into the unit, and it turns out there's so much about quantum computing that you can't actually squeeze it into one lecture. So I thought I'd give a general talk. And as it happens, the Computational Intelligence Society, it's a mouthful, we normally just call it CIS, they actually needed someone to give a seminar, so I thought I'd combine two things. And this is why I also encouraged a bunch of my students to come along. So, because a lot of the stuff I'm covering here, and particularly some of the cool videos, I won't actually be doing in the lecture, because on the lecture I'm really going to be focusing on computability and complexity. And I'll get it out eventually. Okay, so my background in quantum computing is I've done some research for basically this lecture on this topic, and specifically as it relates to TFCS. So I'm not a quantum computer expert. I do not understand all of quantum physics. According to one of my friends who's a physics PhD, there's about 3 people in the world that absolutely totally understand quantum physics. And he's basically one of the guys he's working with is a Nobel laureate, and he doesn't either because it's not his field, you know. So does anyone here fully understand or have a basic idea of quantum physics? Let's put it that way. There's a basic idea? Yeah, okay, good. There's some major concepts to know. You need to know the idea of quantum uncertainty. When you talk, you need to know things like superposition, tunneling, entanglement, all these wonderful terms, and we'll get to all of those. But because I'm not a full expert, I'm actually going to cheat a little bit, and I'm going to pass on some of my research by the use of videos in here. So there's like a bunch of slides where I'll talk about stuff, but there's also some slides where I'll just press a button and some other people will talk about stuff instead. And you get pretty pictures at the same time, so hey, that's probably a good thing. So, on with the show. The whole idea of computation is that it can do things that maybe we otherwise wouldn't be able to do, or wouldn't be able to do as quickly, as easily, or whatever. Normal computing does have its limits, and sometimes they are quite surprising, depending on whether you know the halting problem or not. If not, please come and join my TFCS class sometime. So there are hard limits to what normal computation can generally achieve. There's things that we just can't do. There's other things that actually you can do, but they're very, very difficult as the problem becomes larger. So that's talking about computability and complexity. So computation is good, but also has some issues. The general models of computation that we're looking at, such as Turing machines, etc., normally assume that you're computing one instruction at a time. And that's fairly standard, and that's fairly simple, and that's not necessarily what we do. But the good thing about quantum computing, so the good thing about computing in general, is that it can do one thing at a time really darn quickly. So whether those things you're doing quickly are the right thing or not is up to the skill of the programmers, which is going to be mostly you guys in the future, of course. So yeah, lots of fun. And this is probably my favorite quote about computing. So from there these days, of course, we don't bother doing things one at a time anymore. We were doing all sorts of things about sharing processors and getting multiple instructions through per clock cycle or whatever. But these days you actually have multiple processing cores in a standard desktop computer. And if you look at the supercomputers, not only do they have really, really fast and really powerful processors, but they also have quite a lot of them. For example, the IVEC computer just across the road at Technology Park, called Formax, that's one of their new ones, that does a lot of operations per second, depending on whether you are talking the European or the American. That is 62 billion for European, or 62,000 billion for American, I believe, because there's a bit of difference as to what exactly billion is. Now, that's really good. Some people initially said, well, look, quantum computing, do you actually want it? Particularly Mr. Cray, and yes, Formax is actually a Cray computer, which is now a parallel computer. But parallel processing definitely has its uses. Still, there are limits. There are things which are a little bit difficult to do. For example, you have a look at the problem called the Dawkins weasel. Very simple problem. This came about the very popular saying, which I'm sure you've all heard: if you have an infinite number of monkeys in a room with typewriters, eventually they will type out the complete works of William Shakespeare. So, yes, that's exactly the point. That's the point of Dawkins weasel. What the problem there is to say, okay, how hard would it be for the proverbial monkeys that you just get one monkey, one typewriter, typing out random things, and how long would it take them to say, to type out, methinks is like a weasel? Which is a bit weird, but that's the problem. How long would it actually take? Well, the thing is that there are apparently 10 to the 40 possibilities of doing that. We're not talking about the works of Shakespeare, we're talking about one simple, very nonsensical sentence. What does that mean? That means if Formax is checking every possibility rather than using some smart algorithm, Formax wouldn't get around to necessarily finding this before the universe ends, given the current estimate on the lifespan of the universe, etc., etc. So what we have is some very, very simple problems that modern computing can't yet solve convincingly. And by the way, if anyone has any points to make as I'm going through, please feel free to stop me and chime in or whatever. You're less able to stop me and chime in if I'm actually playing a video, but other than that, just say things basically. Now the good news is that in theory, a quantum computer could do this, could look at all the possible solutions very, very quickly. Very quickly. We're talking possibly, microseconds, seconds, whatever. So that is a bit of what brought on all these comments about, hey, quantum computing can do different things, it's a different scale, etc., etc. So that's really what this talk is about. What can quantum computing do? What are we looking at? And perhaps more importantly, what is the current state of the art and what can't it do? And unfortunately, the answer to what can't it do and what can't it do currently is far too much. So what is quantum computing? The short version is it's a bit of insane physics trapped in a box and cooled down to really, really low temperatures. A normal computer, as you all know, uses electronic bit gates and stores information in bits 0 and 1. A quantum computer also uses bits, but they're quantum bits called qubits. Normal bits can very easily be represented just on or off. It's a high value or low value of current. There's a lot of ways which you can generally represent 0 or 1. And you can also represent probabilistic measures, such as fuzzy logic, in similar means. Okay? By having careful control of the current, you can have multiple states rather than just 0 or 1. That's all relatively well understood. It's been around for quite a while. Now, a quantum computer, the qubits, can also take the value 0 and 1. The special thing about a quantum computer is each qubit does not actually have the value 0 or the value 1 until such time as it is observed. In fact, it has both values, strictly speaking. So that is, in a way, the power of quantum computing, and that's the thing that is a bit hard to recognize. This is actually based a bit on thinking about, say, electrons. How much do you guys know about physics? Not a whole lot? A little bit? Yeah. Pardon? A little bit. Are you a physicist by chance? Okay. My physics stopped at high school, so my physics isn't crash hard. Okay. What do we know about electrons? Electrons have a position, they orbit particles and stuff like that, right? Well, actually they don't. That's the thing. The problem is, even something as simple as an electron, when you get down to that sort of size of particle, it doesn't have a strict, yes, this is the spot I am position. It has an area where it is likely to be, or where we think it is. Now that can create some problems. In particular, it turns out that electrons, because they are somewhere within a particular area, well, if that area bumps up against another area, well, the intersections can be very interesting, etc., etc. This is where the whole quantum uncertainty comes in. We don't know the exact position of that particle. And this is the idea with quantum bits. The power here is not in that it might be 0 or 1, because we can just use a probabilistic model for something that could be 0 or 1. The problem is that, for all intents and purposes, it is both 0 and 1 at the same time. That has some very useful applications. Unfortunately, we can't really model that very easily with our circuits, which is one of the big problems with quantum computing. So I'm going to get onto the first video, which is a great introduction, and many of you have probably seen it by now, which is the one from PhD Comics, and is frankly very cool, so I'll just play that.
Well, we use the word in reference to the laws of physics that apply in the microscopic world at the level of individual atoms, individual electrons, elementary particles, where physics is qualitatively different than what we experience in our everyday lives. You ever been to the beach, see waves coming in? Why do the waves have characteristic speed? That's all classical physics. Send a rocket to the moon. There's no quantum physics in that.
We're discussing right now quantum world, which is at the very smallest scale. The elements of reality down at that level are not described by what we're used to, which is the momentum of something or the position. If you were to go and ask the same question at the microscopic level, at the quantum level, then things break down. So things are different there.
And that's a big part of why we're interested in this whole subject. Can we take this quantumness of the microscopic world and blow it up to larger and larger sizes, manipulate them in a way which is highly controllable to get them to do what we want them to do? If you have a quantum system, a quantum computer can do things, can perform tasks that we couldn't hope to perform with ordinary digital computers. You can't dream of doing it. So when we think about how quantum information is different from classical information nowadays, we're thinking about this intrinsic randomness, the uncertainty principle, and also about entanglement. Classical information we can express in terms of bits. You can take any amount of information and just write it as a string of bits. And in the quantum case, we call them quantum bits, or qubits, and they're different from ordinary bits in some fundamental ways. A classical bit, I could write a 0 or a 1 on the table and everybody can look at it the same way. But in a quantum bit, there's more than one complementary way to look at it. So you can kind of picture it this way. You've got a box and you can put an object in the box. In the quantum case, there's more than one way to open the box. And you've got to make a choice. If you open door number 1, you'll never know what would have happened. It cannot be known what would have happened if you had opened door number 2 instead. Those are incompatible things. That's something really new compared to classical physics. That's what I mean when I say it's really intrinsic randomness. It's not that there's some record somewhere, but you haven't looked at it yet. There's no record. It hasn't been decided yet whether it's going to be a 0 or a 1. It's not until you make the observation and open the door that it becomes the value of this bit. Maybe it's a 0, maybe it's a 1.
The randomness comes from the ability of quantum states to be in a superposition, to be both in the state of 0, of definite, like say spin up or some like particle, and also a spin down state. What if they were not just numbers, they were waves, right? And you can like put together 2 of these waves, and you can think of having half of the 0 and half of the 1. So whenever you measure it, you will end up getting half of the time the 0 and half of the time the 1. So superposition is fundamental for that randomness.
If I flip a coin, I don't carry coins in my pocket anymore, or I flip one. I flip a coin, and then I cover up the coin as soon as it lands. You don't know whether it's a heads or a tails, but it's either a heads or a tails. We just don't know yet. That's not a superposition. That's a probability distribution. But if we have the most complete description of the system that is possible, compatible with quantum physics, like when I prepared the state and when we open door number 2, we don't know whether it was a 0 or 1, that's superposition, because that's really intrinsic randomness instead of probability associated with ignorance.
So it takes 2 to tango in quantum entanglement, right? You cannot just have a single qubit and say, oh, it's entangled with what? So you need 2 qubits at least.
The reason these quantum correlations are different than classical correlations is because we have these distinct, incompatible ways of observing the system. Classical systems can be correlated. We can flip 2 coins and they're either both heads or they're both tails. No big deal. But there's just one way to look at that coin. The qubits are different. We have these 2 incompatible ways of looking at them. They have 2 ways to be correlated, either the same or different for 2 different sets of doors. Those are altogether 4 possibilities, and that means the correlations are richer, they're more interesting. And the richness of the correlation increases very markedly as you increase the number of parts or add additional qubits. If you have just a few hundred qubits and you want to write down a complete description of all those correlations among those qubits in terms of classical bits, you'd have to write down more numbers than the number of atoms in the visible universe.
It's one of these things like, I don't know if it was Faust that said it, that achieving perfection is hard, but remaining perfect, that's impossible. A lot of what we're trying to do also creates things that are stable, right? Because you can have the most exotic quantum state, but unless you can probe it, measure it, evolve it in some way that you want, steer it, it's going to be useless.
There's a central problem, and that is if you're running a quantum computation, if you're performing a sequence of operations, processing quantum states, that has to be very well concealed, not just from you and from Spiros and from me, but from the whole outside world. Classically, there'd be nothing wrong with looking in every time step what the state of the computer is. That wouldn't prevent the computer from getting the right answer. But quantumly, if we keep looking at the computer, that will destroy these delicate superpositions. It's a secret computation until the end, when we're finally ready to get the result out. We make a measurement. And then it's okay to tell everybody what the outcome is, to broadcast it to your friends. So we can't be looking at the computer while it's performing the computation. If we ask it afterward, what did you just do when you factored that huge number, it should say, I don't remember, because there was no record left behind of what it was doing at intermediate stages of the computation. And this is what makes it so challenging, because we can't allow any leakage of information from the computer to the surroundings. That would destroy the quantum computer. That's what we call decoherence. It's the big enemy. There's a whole quantum world out there which is largely unexplored, because it's only now, within the last decade or so, that we are developing the technological capability to scale up quantum systems, to manipulate them, and we're not exactly sure what that's going to lead to, but we think it's exciting. And I do get excited.
So that's the PhD.
But we were new to the field. We hadn't heard
We hadn't been part of the discussion.
discussion.
So we were sort of outsiders. We didn't know it was impossible. It's basically I met you in the hall and we
Yeah.
started talking.
Leave that one. So PhD explains it very well. There's a bunch of key concepts. They mention the qubits, they mention the superposition, they mention quantum entanglement, which we're going to get onto now. I'll just put back up to here for a moment. The addresses there, as you can see, they have lots of other great explanations of other physics and science and stuff. Now, in this talk, I'm not going to get into the physics of things, okay? Because, as I've said, the physics is too hard to fully understand. What I want to do is give enough of an idea that you have some sort of vague idea of how the physics impacts the computation. That said, I'm not going to talk about the circuit level stuff and all that as well, although, again, I'll point you in the right direction if you want to go look for that. But frankly, as someone said earlier, if you go to the Wikipedia page, you get a lot of the resources anyway, so, hey. So we've got the idea of qubits, and a qubit is going to be either 0 or 1. And that's really nice. Initially, the qubit is both 0 or 1. Eventually, you observe it, it'll be one of the two. But as it mentioned, a qubit by itself isn't that useful. What you really need is the idea of quantum entanglement. And this happens, like in the physics, in nature, whenever very, very small particles, even very, very small diamonds, for example, interact. What happens is that once you remove the interaction from each other, there is still the results of the interaction as part of their properties. So before they interact, they each have a totally independent state. You can fully describe each one of them separately. After the interaction, when they're entangled, you've separated them, but you can't fully describe the state of one of these without talking about the other particle. So they are now in some ways related. And there's been a lot of very good science fiction written about wonderful things you can do with this, like teleportation and long distance, communication and whatnot. But we're just looking at the quantum physics of it right here, which should be more than enough for anyone. When you've got a pair of particles, whatever they are, quantum entangled, then you could consider there to be a superposition of both of them together. So if one of them can be 0 or 1, in fact it's currently both, the other one is currently 0 and 1, then now that you've got a superposition of the two particles, you have 4 things that they can be. 0, 1, 1, 0, 0, 0, 1, 1. That's very nice. So, but remember, it's not that it is one of those 4 things. Actually, those two particles are all of those things at the same time. What does that mean? Well, let's say you want to check something, and you want to say, okay, we want 500 bits. We want to keep randomly guessing a 500-bit number until we get the actual number. Well, a 500 qubit quantum computer will have all of those values at the same time. How long does it take to guess? Well, it's actually there already. How long does it take to guess is not applicable. Okay? So that is the scary thing when you think of quantum computing. That said, there's a lot more before you get there, and there's certainly a lot more before we'll get there. When you start to talk about entanglement, that's when you start talking about like shared states and that rapid growth, the exponential growth as you add more and more qubits. If you've got n qubits, they are in 2 to the n states at the same time. So we can more or less, in theory, check 2 to the n possible solutions simultaneously. Note that I say in theory because at the moment we can't. Okay? I'll just be blunt about that at the moment. This research follows on from some research started long ago by some rather famous people, some of which you may even recognize. If you're, you definitely recognize Einstein, no doubt. Some of you may recognize Podolsky. I'm sure you've all heard of Schrödinger and his cat. That's also very important to quantum physics. There's many more things I wanted to cover. I wanted to go in detail about Schrödinger's cat, the double slit experiment. How many people have come across the double slit experiment? Yeah, that's a really good thing to have a look at. But again, I'm trying to focus on computing, so I'll leave that for now. That means you have to start talking about waves and particles and stuff, and that sounds too much like physics to me. Physics is hard work, so definitely not me. What I want to look at is what can we do with quantum computing? Okay. Now, if we can compute all these things, if we can effectively have something that's all these states at the same time, what can we do with it? Well, for example, with cryptography, there's two fairly interesting applications of quantum computing, both of which are being very much discussed / argued about in the academic media at the moment, and occasionally it leaks into the non-academic media. That's secure communications and cracking encryption algorithms. They are both applications that people are working on at the moment, despite the fact that the computers to do them aren't fully ready yet. Encrypting communications is very interesting. The idea is that when you observe a quantum computation, whether it's the qubits or the entanglement or whatever, you actually then get what's called decoherence, and the quantum computation will end and you have an actual value. So if you have a quantum communication, the idea is that the observation will produce a measurable effect in the communication, so you then immediately know, hey, that communication was not secure, and we will now cease communicating. In other words, you theoretically have a communication system where as soon as your enemy breaks into the system, you can shut it down, which is sort of nice. Various groups would be very interested in such a system. Unfortunately, there are many arguments going on as to whether or not this will actually work. In particular, some groups say that there are ways to get some information from the communication with only a minimal interference, and if you do that for long enough, therefore you can get enough information to do damage, so it's not totally secure. Other people are saying no, if you do things carefully enough, you can actually measure it. So if you look at the papers and the articles being written, there's a war forming there on both sides. Has anyone come across this so far? Yeah. You've heard about the secure communication? Yes. Note, by the way, that quantum communication at the moment, do you have any idea how long we can do quantum communication? We're talking like really, really short distances at the moment. What? Well, because you need a specific communication channel. That's interesting. I hadn't come across that. Yes. Well, it has to. Yes. We don't have quantum wireless communication yet, which would be a scary thought. I'm not saying, by the way, that is impossible, because I don't understand reality enough to say what's possible or not, quite frankly. So anyway, here is one application that people are really looking at, and maybe the Mexicans are doing quite well there. If you happen to have that reference, please send it to me. We're interested in that. If not, I'll just go have a look at it. The other thing is, a lot of people are making a lot of claims about, oh, we've done this with quantum computers, we've done this other thing. And sometimes the claims are true, and sometimes the claims are somewhere as true as, say, cold fusion. Actually, are you guys at all... Yeah, that's the one, yes. Are you guys old enough to have come across the whole cold fusion thing? And got very rich, basically, and lots of sponsorship and this and that, and they couldn't duplicate the thing, yes, and no one else could duplicate the thing either. And then occasionally, in one lab or another would say, oh yes, we've duplicated that, they'd get lots of attention, and then they couldn't actually produce it, so, yeah. So, be a bit careful about any claims. So that's one of the things, communication. The other side of it is cracking encryption, and of course RSA is yeah. Guess what build I'm paying today. The RSA is a fairly common cipher, and in fact there was a competition open for quite a long time about cracking RSA words of a certain length. Okay, here's a number, please factorize it. And 10 years later, most of the numbers have not been factorized, and not most of the prizes have been claimed or whatever. RSA 1024 is a 1024-bit binary number, which has not been factorized to date, full stop. The prize was offered to anyone who could factor it, $1,000 US. So, hey, believe me, a lot of people tried actually smaller numbers, like half that size, and most of the numbers, even much smaller than that, were not successfully factored. So how hard is it to crack a 1024-bit RSA encryption? Well, actually, pardon? Yes, the binary string finishes at a 2. Well done. Yes. Yes. Go for it, mate. Unfortunately, there's no prize there anymore, but if you found a good way to factor it, you wouldn't need prize money because you would be set up for quite a while. Now, that's by standard computing. People are running things, people use computer farms, and like a Google employee used Google Computer Farm to basically solve some of these after the prize closed, just basically to show it could be done. But even they didn't get close to the 1024-bit one. That's because what you've got to basically do is start trying possibilities. How many possibilities you have to try? Well, the square root of 10,024. So, what about if you had a quantum computer with the square root of 1024 bits? Well, then would that work? Well, actually, you'd need a full 1024 bits because you need to look at the factors. But there's an algorithm called Shor's algorithm. Yes, there are actually algorithms in existence specifically for quantum computing. And if you, again, look on Wikipedia or many other places, you will actually find them. Apparently can do it very, very easily. We're talking about if it's proper quantum computing with enough stability, etc. It may be done in minutes. Who knows, depending on the computer system. So on one hand, we've got general computing, which can't solve an easier problem than this in years, with lots of people trying. I mean, we've got people using Google clusters to try to solve it, and a 1024-bit, not meg, not whatever, bit, qubit quantum computer can do it in, well, let's just say a relatively short time. Obviously, there's some reason to think, hey, maybe there's something to all this quantum computing. For a start, if someone comes up with a truly general quantum computer using the RSA encryption algorithm, probably isn't a good idea for a while. Because, hey, now people can crack it really easily. So, oops, wrong way. Does that mean that we should all stop using in all sort of those pigeonhole encryption principles? And the answer is no. General quantum computing is not there. As far as I can tell, the largest number factorized by quantum computing so far is 143 April last year. There's probably been others, but I haven't found the publications yet. Before that, the largest was 21. Okay? So, we are not in the great danger of having a 1024-bit number factor at this point. However, that said, quantum computing is actually very useful. Having said it's going to be great, but actually we can't do it, let's say there is one or two things we can do. In particular, there's this company called D-Wave. Now, I'm with the IEEE, so I first came across D-Wave in 2010. They were founded in Canada in 1999. Their aim was to do the theoretical work behind quantum computing, work together with other companies that would actually build the machines, make quantum computing a reality. And frankly, they failed. They failed miserably. They didn't get anywhere at all. Okay? 2004, they turned around and said, well, look, we're not getting people take us seriously. We're going to need to do it all by ourselves. Stop working with other people. We're going to do the theory and we're going to do the practice, and we're actually going to build a quantum computer. 2010 comes around. The company's been around for 11 years yet by then and hasn't actually built a quantum computer. And Spectrum publishes an article. Every year they publish technology winners, technology losers. Spectrum is the IEEE General Machine magazine. Every IEEE member gets that. Because, hey, this company's been going for 11 years and it has not yet produced a product. I mean, that's a bit of a problem. Sometimes you say a company may take a while before it starts making a profit, before it's making, but 11 years without a product, that's a bad thing. That said, in 2011 they had their first viable commercial quantum computer. But it is not a general quantum computer. It is a specific computer used for what's called quantum annealing. Okay, so it cannot factorize the RSA numbers unless they can phrase it in terms of an optimization problem. If they can do that, well, then maybe they actually can factorize it. But the next thing to do is have a look at the chip itself. This is the first of the two chips. This is the one that came out in, 2011. It's called the Rania. It's 128 qubits. So on that little chip, there are 128 quantum bits. And that one little chip is, you guys seen pictures of the old supercomputers, you know, that little chip is basically in one of those. Why? Because you have to keep it isolated and cold to stop decoherence happening. So yes, you have it all in this one little chip, but actually you need this huge machine around it. But that's okay. There's a newer version of the chip, which is Vesuvius, which came out, I think, late last year. Might have been earlier this year. I think it's late last year, though. That's now 512 qubits. So we've gone in quite a jump already. And 512 qubits is quite a lot. I should point out, though, that these are custom manufactured chips. And, for example, the one that has been used by, I think it's Lockheed, doesn't actually have all 512 qubits working anymore. It's down to, I think, 490 something working. So obviously they haven't got some things fully working. But that said, they've got these chips and they've sold some of them for ridiculous amounts of money. One's been sold to the USC campus working with Lockheed-Martin, and one's been sold to Google, who are putting it on one of the NASA research facilities. And they're doing funky things with it. One of the things USC did with it, first of all, was to say, hey, we've just been sold a chip for ridiculous amounts of money. Can we, first of all, verify that is actually quantum computing? Are these people maybe just faking it? Because when these chips come out, people said, yeah, Greg, you've got a chip that does something really quickly, but really? I mean, does it matter? Is it actually quantum? Can you prove that? And D-Wave said, actually, no, we can't necessarily prove that it's quantum. So what I'm going to do now is play you my second video. This one is from some of the people from Lockheed-Martin that are involved with using that quantum chip from D-Wave, and some of the things they want to do with it, and some of the things they are doing with it. This one is a little bit shorter than the previous video.
This machine is like a giant instrument, a new telescope to an astronomer. Instead of using it to search for new cosmological discoveries, we're using it to explore the relationship between mathematics and physics.
It's a very multidisciplinary science. We have physicists, which are probably the most common people who work on quantum computing, but we also have somebody who's in applied mathematics.
If you look at reality one way, you see physics. You look at it the other way, you see mathematics, and it's actually both.
We're in that same kind of moment in time where we're looking at the first or second transistor here. There's a revolution taking place, and it's kind of exciting to watch it play out.
It represents a way that humans can expand the knowledge that they have and the problems that they're able to solve.
It's a game changer for the corporation, it's a game changer for our customers, and ultimately it's a game changer for humanity. Computationally, this is the equivalent of the Wright brothers at Kitty Hawk. Quantum information science, quantum computing certainly has the potential to be a turning point in history. This machine is the first practical step that will essentially reset us on Moore's curve.
Moore's law is an observation that the number of transistors on a chip doubles over a certain time period, or the cost of the transistors halves.
But we now know today that there is a limit to how small you can shrink things, how many transistors you can cram onto a single chip.
So that's going to bound human capability for tackling certain problems. This machine offers an alternative.
And this might be considered a rebirth, maybe, of analog computing for solving certain kinds of problems.
Optimization is searching for the best possible answer among a large set of answers.
These are the kinds of problems that cannot be solved by calculations with classical digital computers.
For example, it would take many times the age of the universe to try to identify the folded state of a protein. And yet nature can do this in seconds, or maybe minutes. It's had billions of years to think about it. We're trying to solve similar kinds of optimization problems.
It mimics nature to find the minimum or the maximum of a design space.
If we can simulate 20 years of evolution in 10 nanoseconds, then we could evolve our engineering systems to be much more successful than what they are now, and it would cost very little. If we actually tried to do that in reality, the cost would be horrendous, and the amount of time it would take would be intolerable.
The most important thing to remember about ordinary computers is that they work with bits, which can be either 0 or 1. In quantum computing, the fundamental unit of information is not a classical bit of 0 or 1, rather it's a qubit, a quantum bit, which can be in a superposition.
Superposition means that the system is in some mixture of the 1 state and the 0 state.
And as a result of that, when you have a string of these quantum bits, you get a multitude of possibilities. So if you have 2 quantum bits, you have 4 possibilities, 0, 0, 0, 1, 1, 0, 1, 1. Those all coexist. And a quantum computer can parallel process all these possibilities.
The idea of a quantum computer is that you build it based on quantum physics, the physics of the very small, rather than classical physics, which is the physics of the large world we see around us. When you get down to smaller scales, things become probabilistic, things interact with different physical effects than the ones we can see on the large scale, or those physical effects manifest themselves in different ways. Quantum computers exploit these probabilistic phenomena in a way that makes a new kind of problem solving possible.
Let's say you're climbing mountains, and you're looking for the deepest valley in this mountainous landscape.
Probably what you will do is begin to walk downhill, and you will continue to walk downhill until you start to walk back uphill. You'll say, I went through the minimum, and you'll turn back around until you find that one point where you're not moving up or down, but you're just stationary. And you can think of ground state as being that lowest possible energy state.
In quantum mechanics, we're allowed to perform something called tunneling. We can literally go through walls.
With this particular machine, it's based on a simulation of this thermodynamic process that includes quantum mechanical effects that allows it to continue to explore the space around that valley without actually climbing up and over and being restarted, but to essentially tunnel through the mountain and find out if there is actually a lower valley on the other side. And it will continue to do that until it reaches the ultimate lowest valley.
It's always an interesting one to explain to a layperson, because it's one of the really weird things that happens with quantum mechanics. And the fact that you have weird things happening in quantum mechanics is because you can exploit these effects that you don't have in your toolbox when you have a classical computer.
There are a lot of problems that are provably very hard, NP-complete or NP-hard in the jargon.
And you want to use the shortest path possible, or you want to route things in a way so that they all arrive simultaneously. So you're looking for an optimization in terms of time management or resource allocation or minimizing path lengths.
Of course, people have been trying to solve them with clever heuristics for half a century.
Using a quantum computer, we would hope to be able to develop algorithms that allow some improvement in the calculations of these problems.
It allows us to consider problems that prior to today have been beyond the scope of anything that we thought was possible.
Problems of energy, healthcare, transportation. The list of problems that we're all familiar with, those can all be eventually solved.
The idea of having hardware that can essentially drive straight to the solution, perhaps better than our clever heuristics, is really attractive.
It's our mandate, it's a moral, ethical requirement that we look at applying those capabilities to where they will do the most good in the future.
Okay, Lockheed-Martin. basically, some of that you'd seen before. There's a few concepts that they mentioned that I haven't mentioned before. I don't think I mentioned quantum tunneling before this, but I'll get back to that in a moment. That's a very useful thing when you get to optimization. But there's a couple of very interesting things to notice in that video, apart from the fact that you've got some basically fairly big companies, successful companies spending a large amount of money, putting a lot of resources into this, which tells you, hey, at least they're serious about it, which is a good thing to know. So that's one of the reasons to know that they're involved. What did they say about, this is the test after the video, by the way. What did they say about how they can solve optimization problems? Did it match what I was saying before? Because with general quantum computing, hey, you've got all the possible answers, so why do you need to actually go step by step to optimize stuff? They talk about going step by step optimizing stuff. That's not quite the same, is it? What they have is the D-Wave chip. The D-Wave chip is not a full quantum computer. What it is something that's very good optimization. But that's where the question comes from. Is the D-Wave chip actually using quantum computing, or are they just doing something funky that's, something new, or some variant of the classical thing, and they're just getting some nice advertising for themselves? That was a big question, and that's, that was an open question for a while. So the chips aren't used for general quantum algorithms. You can't call the D-Wave computer a general quantum computer, which means it can't just check everything at once, get the answers instantly, etc., etc. Although there's problems with that anyway. What the D-Wave chips do is the quantum version of simulated annealing called quantum annealing. Yes, very, very hard there. Even worse than that, it hasn't actually been confirmed that what they're doing is actual quantum annealing and not just something funky with the normal simulated annealing. So it hasn't been 100% confirmed. So I've got a mathematical background. Physics tells me that if I lean against the wall, there's a chance I'll actually fall through the wall and appear the other side. The chance is really, really small. I'm talking about if we all do it for entire lifetimes and everyone in the history of the world did it, it probably wouldn't happen to one of us, but the chance is there. This isn't anywhere near that level of certainty. But there is some good news for D-Wave. First of all, those USC people who've been working with Lockheed-Martin have actually studied the chip, and they've said the thermodynamic characteristics, all the characteristics they were expecting to see in a quantum computer, the D-Wave chip exhibits those characteristics. Now, they've paid for this chip, so, they'd probably be a bit unhappy if it turned out not to be vaguely accurate, but they've said, yeah, okay, it looks like what we've got is actually a quantum computer. This isn't a guarantee. They can't say, yes, it is, but they say, hey, look, it matches all the signs we can look for, so until we can find out new signs, well, the best we can do. Also, they tested some performance. The new one, the 512 qubit, well, actually it was less than that, because, like I said, by then some of them weren't working anymore. They competed at, first of all, they did a competition between that and an IBM high-performance computer. So we're not talking about like a, world-ranking supercomputer. We're just talking about a fairly grunty machine. And they just did some optimization tests. And it matched the IBM machine for 2 of those 3 tests, getting relatively similar performance. In the other test, it beat the IBM machine by a factor of over 3,000. In other words, the IBM machine took about an hour. The D-Wave computer took a very short amount of time, about half a second, which is actually a fairly significant result. That said, what you're doing is you're testing a specific annealing device against a general computer. So it's not necessarily a fair test, and the paper points it out to be fair to them. But still, it does mean that at least there is some performance even at this early stage. We're talking about a very early stage thing. So it's not all bad for D-Wave. In fact, if you look at the papers that are coming out of USC about this, they've got papers on actual protein folding, which is what you saw in the video there. They're doing that with a quantum computer, and they've got a bunch of other results as well. So there are actually some very positive signs there. It's not saying that, hey, quantum computing is wonderful, but it's saying, hey, quantum computing actually is already not too bad, and we're only just starting. I don't know whether I've still got this in here, but there's a more recent study has actually said that that computer, if you're talking about the sort of processing power it has, it roughly ranks 10th in the world's list of supercomputers. Which isn't bad for basically a company's second attempt at chip. I haven't had a chance to read that study, I only came across that this morning. But it's another USC study and people interpreting that data and whatever. I would take that with a grain of salt, but all of this adds up to enough seasoning to say, hey, there is something here. Okay, there's something that we probably should have a look at. And even with just doing simulated annealing, there's some funky things you can do with it. For example, quantum tunneling is a really wonderful thing. The idea of quantum tunneling is that when you have a wave and it's a barrier, there is a chance that some of that energy will actually pass through the barrier. You can have the wave keep going, just it's very damped at lower energy level. And depending on the thickness of the barrier and various other effects, sometimes actually very energy can pass through, depending on exactly how it works. These pictures are from Wikipedia. Because, hey, Wikipedia has the best pictures. And by the way, the notes to these slides have a bunch of annotations and sources and stuff. I am stealing from various places, but at least I'm referencing to where I'm stealing from, because otherwise my students will tell me off for, being inconsistent or whatever. Quantum tunneling was discovered by Friedrich Hund, and it's a really cool thing, which basically says that when you have a particle and it hits a barrier, well, because the particle doesn't actually have a particular position, there's a chance that, well, the particle's actually on the other side of the barrier already. Think about that for a moment, okay? You've got the particle on one side of a barrier that it can't get through. It bumps up, so its position is probably somewhere against, actually no, it's on the other side of the barrier, so. We knew it definitely wasn't, it was definitely on this side, now it's definitely on this side. Somewhere. So that's the really cool thing about quantum tunneling, and I've got a video on that coming up shortly. But this is one of the things that it actually makes the D-Wave computers very cool for simulated annealing, because they can use this. Rather than having to say, okay, there's a chance we go back uphill, there's a chance we take a bad step, they just say, there's a chance we're going to go right through the hill and find another minima at the same level, or maybe even lower. Think about a simulated annealing algorithm where you don't actually have to step back up to get long-term optimality. So, I mean, just that one thing already gives you a fair bit of improvement. So if they have nothing else to do with quantum computing, just quantum tunneling, that's actually not too bad. So that is one of the things from Lockheed video, and I'll just play you a very, very brief video to try to explain quantum tunneling a bit better.
Suppose you drop a ball down the side of a valley. Classical wisdom tells us that when the ball rolls up the hill on the other side, it can't go any higher than the height from which you dropped it. That's conservation of energy. Even if there's a nice big long slope to roll down on the far side of the mountain, the ball just can't get there, unless you give it enough energy to get over the barrier. But in quantum mechanics, things work a little differently. You see, the quantum world is probabilistic, so if you release a particle in a valley, chances are the next time you see it, it'll still be somewhere in that valley. But if there's a nice big slope to roll down on the far side of the mountain, well, that's a place the particle would really like to be. And it turns out, there's also a small chance that's where you'll find it. If this isn't crazy enough, it's even possible you'll find the particle in the middle of the mountain. And in real life, this means that an electron sometimes hangs around inside the nucleus of an atom.
Now, if that doesn't make your head hurt, I don't know what will. Which is one of the reasons I included this. So, yes? Okay. No, I'm not sure whether we call the D-Wave computer quantum computing either. However, that said, people who know more about it than me have said yes, it meets all the hallmarks. So my comment, I think, was more along the lines of, if that's the only thing it can do for simulated annealing, it does the normal simulating plus quantum tunneling, that's already a nice step for simulated annealing. I think it does more than that. If you actually have a look at what it does, and I'll go into a little bit more detail of how it does it. Basically, they use this system they call tuning. So they tune in these qubits slowly, one at a time, to try to optimize it. I'm not sure how that tuning works, so they actually have a couple of videos on it. I still don't know about how it works, which is one of the reasons I haven't included it. It's on their hardware. But basically, that's how they do their optimization. They slowly tune in various levels and get more and more optimal as they go through. Again, to me, that could just be you putting values into variables, whatever, but obviously whatever they're doing seems to be working fairly well, so, you know. But yeah, that tuning, to me it seems sort of familiar. There's quantum tunneling, you know, in terms of something like simulated annealing or whatever, is interesting. With simulated annealing, you actually have to find the place first. This one here just says, well, okay, it could be anywhere. Well, let's tune it to be in that valley rather than tuning it to be here. So I don't know if that helps at all, but yeah. I didn't actually know there were any things using quantum tunneling, but there you go. Again, I was looking at the quantum computing. Okay. Oh, lovely. Oh, there we go. I've just learned this wonderful new concept. Turns out I've been using it for years. Like I said, I'm a wonderful expert in quantum computing, you know, hey. So what you're saying is we've all got quantum computers in our pocket all the time. Maybe we could charge, like, why don't we charge Google for 20 billion for it, you know, hey, we'll be rich. Okay, so that blew my mind, but apparently not everyone else's. The point is, quantum computing has some very distinct concepts, and Wally can understand them, so maybe we have a chance as well. Like I said, I found one that was very appropriate. I haven't really said a whole lot about quantum computing today. What I've basically said is, hey, there is a reason that as, especially computer scientists, we should be interested in quantum computing. And there's reason to believe that steps are being taken at the moment towards it. That's about all I can say about quantum computing. I can't say yes, it's here, because frankly we have no proof. I can't say it will solve all our problems, because it won't. From a computability point of view, I'll jump to something we're going to talk about in TFCS. It does not add anything to what we can compute. Anything that is computable on a normal computer, well, maybe I should say anything that's computable on a quantum computer is still computable on a classical computer, in terms of yes or no. The thing you get with a quantum computer is, for certain things, it's just so much faster. So if you're looking at computability versus complexity, a quantum computer won't actually help you for computability, which actually blew my mind when I found out about that. I thought, wow, you must be able to do lots of things. Actually, no, you can't. What it does do is some of those things that are NP complete, that, you know, or NP hard, it would be actually really, really difficult to solve big problems. Well, that's suddenly something that maybe we could do realistically in the future, which adds something totally new. Does that mean P equals NP? I'll be asking that possibly in the exam now. But hey, I think I actually have a question vaguely like that, or was that last year? Anyway. Okay, well, thank you for coming. You've filled in enough names that IEEE would be happy. Are there any questions that I could possibly even answer, or maybe other people in the audience could answer, for that matter? Yes. Well, until a few moments ago, I didn't know USB drives use quantum tunneling. So, what they're doing there is they're basically using probabilistic method anyway. So they're not relying on it. They're saying if you do it for long enough, it'll eventually happen. And just like, you know, simulated annealing. The idea, you know, hill climbing search. You basically keep going. You look to see you're going up or down depending whether you're minimizing or maximizing. You keep going until you find a maxima or minima, whatever you're looking for, and that is a point that's good. But the problem is the next hill along might be bigger. The problem is you have to climb down to get back up to it. So a normal search won't find it, but a simulated annealing search, it mirrors what, for example, crystals do when they're cooling. They all slowly line up with time. So simulated annealing basically jumps, and jumps less and less. And the idea is eventually it will stabilize into that minimum state he was talking about, that optimal solution. And theoretically, if you do the cooling slowly enough, you will get the optimal solution. Problem is, slowly enough could be, you know, for the next 10,000 years, but we won't mention that bit. So that's, you know, that's where it's a probabilistic method anyway. So using another probabilistic thing, hey, that's great. Use it for something like USB. I wouldn't like to think that my USB drive will suddenly appear out there, but it might. hey, that explains why they always go missing, isn't it? They do a quantum jump to somewhere else, right? Yeah. Do you know what probabilistic it uses? What probabilistic methods it uses? Basically, there's actually other, like quantum-related stuff. I mean, quantum science has been around for quite a while, but quantum computing itself is still, well, I mean, the D-Wave chips are the first commercial, so-called commercial, computer chips to be sold anyway. Anything else? Let me just pause the recording for a while. Well, look, to be quite honest, as I was writing up this talk, I was saying, wouldn't it be really funny if, as I'm storing this and backing it up on the web, somewhere there's, the CIA, whoever, intercepting this saying, if only he knew what we've already got, etc., etc. Bingo, yes. Well, I mean, but what I thought is, if someone actually comes up with that, it would be such a strategic advantage you wouldn't tell other people. Yeah. Yes. When you try to publish it. Yes. Quite. They did nasty things to him. But the recent analog would be the 3D printed gun, where the guys designed the 3D printed gun and published the recipe for anyone to print, and people said, well, take it down, you can't do that. They said, oh, okay, we'll take it down. But by then everyone had it, so you could find it all over the internet now. The cat's out of the bag. Yeah, I think my official position on behalf of Curtin University is, I'm sorry, I can't comment on that. Yes? Yes. Yes. Actually, there is such a thing as a universal quantum Turing machine. And there has been actually quite a bit of proof done about that. And that's where I'm saying they've looked at quantum computability, because they've got proofs of Turing computability, and they've shown that that is equivalent to quantum computability. Anything that's computable with a Turing machine is also computable with a quantum Turing machine, and vice versa. Just the rate is different, basically. So the Turing machine, once again, is shown to be very stable, which is good, sort of. Yes? Yes. Yes. As I no, because that's that's recording it. I actually, as I mentioned earlier, had a few extra slides in this presentation. The slide I had just before this slide basically lists a bunch of challenges with quantum computing, and that was the main one I listed actually. Once you've got your wonderful quantum computer, and once you have the full entanglement, everything there, how do you choose a state? Now, D-Wave have solved this. They are choosing the state using the tuning process. So I'm guessing the first steps might be, rather than, yes, okay, we've got everything simultaneously, but let's slowly find out which one we actually want. So basically, even if it theoretically has all the states, so therefore we've already solved the problem, the process of getting to the answer might be a little time-consuming. And that would probably then be a lot like the genetic computers, where actually formulating the problem and reading the answer takes much, much longer than actually generating the answer in the first place. So
it's like, I have this computer to generate all the answers, but in order to get it, I just need a normal computer.
A lot of people have made comments about D-Wave's computers along the lines of, wow, there's this 20 billion computer that could do what mine could do, woo, But, I mean, think about it this way. We're talking about a second generation computer, actually probably still first generation, because they haven't really done a whole lot different from the thing. And at the moment, it's still a baby. It's still that big box with a vacuum tubes, which has a moth flying into somewhere to load up a computation punch cards. Okay, give it another 10, 20 years, see where it is then. But yeah, at the moment, it's not particularly sensible. You're quite correct. not when baby's a 20 million machine owned by the biggest manufacturer of weapons in the world. Did you notice how they're talking about it's a moral imperative that we do all these wonderful things? Yes. Yeah. Absolutely, you know. Look, let's all be very clear on this. It is in everyone's best interest to promote peace, prosperity, to make sure everyone's well fed, good transport. Because when there's peace, prosperity, more people grow, we're all happier, population problems happen, wars happen, you know, hey. Or crusade if you prefer. Yeah. Aeronautics, yeah. They've got their fingers in lots of different things, but basically yes. So yeah. Well, they didn't build it. They just bought one. Well, think about it this way. Who are the two people? Think of the other people that have the quantum computer, NASA. What do? They fire missiles. You know, hey.
All the enemies are either in the light or dead state.
Well, what we're talking about here is Schrödinger's cat, of course. Yes. Okay. Guys, we can have fun discussion while we're eating biscuits. So, are there any more questions pertaining to the talk? Yes. And they're all entangled and everything. Yep, fair enough.
Is there a sort of an analog type, sort of like a CPU that's actually doing the computations?
Yes. There is a very good. If you go to the D-Wave website, they've got about 3 or 4 different videos which show all the breakdown of how they did the computers and how things work, and actually talk about materials things are made out of, what the barriers are used, all that sort of stuff. It's actually very cool. That basically they've got layers of the qubits. They build individual qubits. They layer them, they stack them on top of each other, and then they actually have conventional computers around that to basically interact with them, to basically tune them and whatever. So yeah, think of them as like one of the specific process unit, maybe like a GPU or something like that. In this case, a QPU or something, and the rest is there to feed it effectively. Anything else? Okay, well, thank you very much for turning up. I hope you'll assist me in